Right, we are here today at SAP in Palo Alto with one energy efficient model and one typical house to explain global warming to young kids. And we'll start over here with the materials we used. The first one here is asphalt shingles, which is on the majority of homes here in America. It has very low solar reflectance, so it absorbs a lot of the sun's energy and absorbs it and re-radiates it into the property. This is not a sustainable roof. If you're in a hot climate area like Sacramento or the Tri-Valleys, a roof like this will typically last you between 10 and 15 years. Then it will be torn off and discarded in a landfill. These are not biodegradable, they don't break down, and the solvents leach out and can get into water streams. And also, asphalt has a number of known carcinogens on there, so as it heats up, it does off-gas a little bit, although there aren't any concrete proof that people have actually got tumours and cancer from this. But this is your standard American roof, direct to deck, very low solar reflectance, energy absorbed right through. Now this is also your standard American wall, fiberglass bats insulation in the walls, wood framed siding, and this also is not very efficient as well. If we put an infrared camera on this, the energy will go right through. The wooden studs is where we see thermal bridging. We see compressions in the fiberglass, so we get air movement and cavity convection. And as soon as we get that, the R value can drop 50 to 75%. So this is your standard American home, which from an energy efficient standpoint is not very energy efficient at all. We did a surface temperature reading on this a couple of days ago in San Jose. The ambient temperature was 90 degrees. We measured the surface temperature of the asphalt shingles at 175 to 180 degrees Fahrenheit. So that essentially means all that heat is eventually going to transfer into the building and heat it up. Now where the problem is that when the property heats up, you need to cool it down with air conditioning, and the air conditioning requires electricity from power plants. And fossil fuel power plants are some of the biggest generators, if not the single biggest source of carbon emissions right now. And if we look at this little diagram right here, we've explained it that approximately 50% of all the electricity used in properties is on heating and cooling. And as the property heats up, air conditioning goes up, and as air conditioning goes up, the power plants must burn more fossil fuels to meet the demand to run these cooling systems. The problem is that when you've got millions of homes at the same time running their air conditioning systems, these guys get overtaxed and overburdened, and they're burning more fossil fuels to meet the demand. As more fossil fuels are burned, you have more carbon emissions, nitrous oxide, sulfur dioxide, and mercury gas going up into the air and polluting the atmosphere. And this is the principal cause of greenhouse gases. It's not car emissions, not here in California anyway. It's fossil fuel power plants. Now some of the other problems with the fossil fuel emissions is that they also contribute to acid rain, urban heat islands, deforestation, and heart and lung problems. And one interesting thing is a lot of people have wondered why they have so much mercury in their body. Well, one of the reasons why is mercury is also a gas which is off gas from the power plants, goes up into the air, falls over water and plankton. Little fish eat that, bigger fish eat this little fish, then us as humans eat that fish, and we take the mercury in because of this situation here. What the solution is to simply try and figure out ways to attack this 50% problem here, and we can do that by cooling the building envelope down with heat reflective coatings. We can put reflective coatings on the roof, the walls, the interiors, and the pavements. And recently, President Barack Obama's Energy Secretary Stephen Chu came out with a statement throughout the United States and the world saying that everyone should have a heat reflective roof and have cool colors on their properties. So this is an example of what isn't energy efficient. One of the problems, asphalt shingles, fiberglass insulation, just generally bad design construction. What we're doing in here is showing what type of materials we used on this, which is your typical hothouse and American house. Normal paints absorb energy, they don't reflect it. Asphalt shingles absorb energy. The fiberglass insulation is often ineffective, and as a result we get more global warming. Now if we move on to this house here, this is an energy efficient house, and we'll start off here with the roofing system. This is heavyweight concrete tile. The tile was taken from a landfill for this particular project, which makes it sustainable. And whereas we had an asphalt shingle roof on the other side, which is 100% not sustainable and will eventually be torn off and thrown in a landfill, this one here will last essentially forever, providing you can just keep coating the tile. So this is very sustainable. What we have on here is a heat reflective terracotta tile coating. Has a solar reflectance of 45 to 50, emissivity of 90. So that reflects approximately half of the sun's electromagnetic radiation away. And because it's a heavyweight concrete tile also has thermal mass, which means it stores energy and slowly dissipates it. So far we have two thermal barriers here. We have the reflective coating on the tile roof, we have the thermal mass of the concrete, and we also have convection underneath these tiles, providing that the ridge caps are vented. When air heats up, it rises. So any air that would get through here would be convected out, if you can see through here. On the asphalt shingle roof, the shingles are direct to deck, so there can be no convection. But on this one here, with counter batten systems or above sheeting ventilation, we can convect that air out. So we have three thermal barriers right away here. We have another interesting innovation right here. We used a TPO membrane for our waterproofing membrane. We did that for a couple of reasons. One, this has a Class A fire rating, so if any embers get sucked in underneath there's a very good chance that it won't burn the property down. In California, there are many fires every year, and many tile roofs burn down. What happens is the embers get sucked in underneath here, and as soon as they get sucked in here, they ignite with the black waterproofing paper, and they just burn down. And because you can't cut vents in the roof to help alleviate the fire, often these roofs are just left to burn down. But with a Class A fire rating on this membrane, the chances of the house burning down are a lot less. And also, this is a waterproofing membrane. It's also a heat reflective membrane. So in essence, we have a fourth thermal barrier, and this also has a waterproofing membrane. We have 1 inch of insulation foam under here, and we have a radiant barrier, which you can see up there, which is the metallic foil. So with this roofing system, we have 5 thermal barriers to prevent heat ingress. And most of the energy that enters into a building will come through the roof first, and then the walls second. And all we're really doing is we're swapping out one material, putting a reflective coating on, and everything changes. It goes from highly non-energy efficient to highly energy efficient. What we have here now is a reflective wall coating. Now, it doesn't necessarily have to be white like this, but this white coating has a solar reflectance of 85 and a thermal emittance of 90, which means it will only be absorbing about 15% of the sun's energy. And we can show this under an infrared thermal camera, which we'll be doing in a little bit. Under an infrared camera, this will be